Here we're going to work an example with the conservation of angular momentum. And we're going to look at a problem from last year's final where you're given a rotor-stator combination in a radial turbine as shown, and I'll draw the turbine here in just a second. Water enters the motionless stator at 20 cubic meters per second with no tangential velocity and is deflected 10 degrees as shown. The water then enters the rotor, which turns at 120 rotations per minute, where it is deflected again before exiting at the outer radius. You can assume ideal flow and that the relative velocity exiting each stage is parallel to the blade edge. The radii of the components are shown. Again, I'm about to draw them. And you can assume that the outer radius of the stator is exactly the inlet radius of the rotor, even though obviously in real life there would be a small gap between the two. What we're going to do is the following. Part A, we're going to find the velocity of the water as it leaves the stator. We're going to calculate the torque on the stator. And we're going to calculate the power being transferred at the stator. And then we're going to design the rotor by finding both the inlet and the outlet angles in parts B and C to specified parameters here. So with that in mind, let's draw what the geometry looks like so we can have a better idea of what's going on here. Now, a stator has the same root as static, so by definition, a stator is a motionless part. And in this case, let's see, I'm going to draw it in, here we go, I'm going to draw it in black. So water enters the center of our system, and it goes through the stator, which deflects the flow by 10 degrees. So the stator is not turning at all. The flow, which I'll draw in blue, comes out radially like this, and then it goes through each of the blades and is deflected by 10 degrees. After going through the stator, it then enters the rotor, which I'm going to draw in red. And of course the rotor is rotating. And I'm not doing the greatest job of drawing it here, but it's just the same size as the stator right here. And it's turning with some angular velocity, which I believe I said was 120 rotations per minute. And it's going to have blades that look something like this. So in part B, we're going to find the angle of the blade here, which I'll call phi1, such that the flow relative to the rotor, so in the moving reference frame of the rotor, is parallel to this leading edge as it comes into the rotor here. Now if we look at this rotor-stator combination in profile, we'll see something that looks like this. We'll see the stator blades like this. And there's some little doohickey there that helps make the flow flow evenly into the stator. And then we have the rotor blades that look like this, so that water is coming in like this, turning through the rotor like that, goes through the rotor where it deflects in the circumferential direction, and then out through, eventually out through the rotor like this. Now the dimensions, I said, will be given to you. And let's see, the inner radius of the stator is 0.5 meters. I'm going to erase one of these arrows here so that I can write it in. So this is 0.5 meters. The outer radius of the stator here, and I'm going to get rid of this little stator vane so that I can write 0.8 meters. And then the inner radius of the rotor will also be considered 0.8 meters. And the outer radius of the rotor will be 1.5 meters. That's the radius all the way from the outer edge to the inside, not just the thickness of the rotor there. And then finally, the depth of everything, or the thickness of everything, is 0.4 meters. Now, 20 cubic meters per second is probably a little bit optimistic for a rotor-stator combination of this size, but this is what I have. The numbers work out, and this is what I have in my example. So we're gonna go with it. It's not terribly out of the range probably. So let's look at the first at the stator, part A, which asks us, find the velocity of the water, both the radial and tangential components, as it leaves the stator. Calculate the corresponding torque on the stator. What is the rate of work transfer? Okay, so let's start a new page here. And get our color. We want it in black because we've drawn the stator in black. And let's look at a close-up of one of the vanes of the stator. We know that it's going to turn from the radial direction by 10 degrees, we're told. We know that the inner radius is 0.5 meters, and we know that the outer radius is 0.8 meters. We're going to draw, let's see, the first thing we need to do is draw our coordinate system, which I think we all understand by now is going to be r hat in the radial direction, theta hat in the circumferential direction, and z hat by the right-hand rule in this case comes straight out of the screen. Now we're going to make some assumptions, pretty straightforward ones. We're going to assume incompressible because we're dealing with water. We're going to assume ideal flow because we were told to do that, and as far as first approximation goes, that will give us a perfectly fine answer. We're going to assume steady in the mean, so even though the flow right at next to the blade might not be the same as the flow on the other side of the blade, on the whole, we can take the whole system as being steady. So in general, we know that the velocity, the absolute velocity in the stationary reference frame is equal to the velocity due to the moving reference frame plus the relative velocity of the fluid with respect to the reference frame. But by definition, this is a stator, so therefore there is no velocity of our reference frame, and so the absolute velocity is the same as the relative velocity. So that means that we can use the conservation of mass to figure out what the velocity is at the outlet of our stator. If we were to draw a control volume around our stator, just our stator, then we can show that because the flow is incompressible and steady, we know that the mass flow rate at the inlet has to be the same as the mass flow rate at the outlet of our stator. But we've defined the volumetric flow rate, Q, to be 20 cubic meters per second. So we know that the mass flow rate in has to equal the mass flow rate out. And the mass flow rate out is just going to be equal to the integral over the outer surface of our control volume of the density, come on, pen, times the velocity dotted with the normal direction integrated across the area. But our normal vector to the outlet is just going to be r hat because it's a radial device. And so that means that this is just going to give us the density times the velocity times the r component of velocity times the area of the outlet. And so we see that, right, so if we divide both sides by rho, then we can show that the volumetric flow rate, Q, is just equal to the radial velocity of the flow at the outlet times the area. And so VR equals Q over A, which equals 20 cubic meters per second over the area of the outlet, which is 2 pi times 0.8 meters, which is the radius, times 0.4 meters, which is the height of the rotor into and out of the board in this particular case. And we do a little bit of math with our calculator. 20 divided by 0.4 divided by 2 divided by pi divided by 0.8. And we see that the outward velocity, VR, is equal to 9.947. I'm going to keep 3 decimal places because we're going to carry this through. We might need it to that accuracy later. Meters per second. That's VR. That's not the absolute speed. That's just the velocity in the radial direction. From the geometry, though, we can see that if we draw the flow coming out like this, and VR is the velocity in the radial direction, V theta is the velocity in the tangential direction, and V, the outlet velocity, is like that. Because we know that this is 10 degrees, we know that V, the speed, has to be equal to VR divided by cosine of 10 degrees, which is equal to 10.10 meters per second. And then V theta has to be equal to V sine theta, which is going to be, let's see, 10.10 times the sine of 10 degrees, sine, and that gives 1.754 meters per second. The torque is given as the integral over the control surface of rho times r crossed with v times v dotted with n hat integrated over our area. At the inlet, we know that the flow is entirely radial, so the r cross v term evaluates identically to 0. So we only need to evaluate this at the outlet. Now r cross v is just going to be equal to, well, let's do this formally, right? Torque is a vector. So this is going to be the integral over the outlet of the density times the r vector, which is just the radius at the outlet, times r hat, crossed times the velocity, which is going to be, I'm just going to write it as Vr r hat plus V theta theta hat, which we just solved for above. And all of that times the velocity dotted with the outward pointing normal. Well, the outward pointing normal is r hat. So we know that V dotted with r hat, V, the velocity dotted with r hat, is just going to give us VR. And because they're both in the same direction, we're going to get r dotted with r being positive. And all of that integrated over the outlet. Well, and I'm I'm just going to do this formally still. That means we're going to integrate over the outlet of rho. Let's see, r hat cross r hat is identically 0. So we're just going to get the radius of the outlet times v theta. And we're going to get, let's see, an r hat cross theta hat is going to give us a z hat. And so we have all that times vr. And now I'll put my z hat here. dA. But because we've assumed steady in the mean, when we do this integral, we end up with, let's see, the rho carries through because it's constant. But if we integrate VR over the outlet area, well, that's just going to give us Q, as we saw above up here, where VR was equal to Q divided by the area. Well, that means that Q is equal to VR times the area, and because we're assuming steady in the mean, we can do that integral straight away to get Q. So that takes care of rho, VR, and the dA part, and so then we just have to multiply this by the radius of the outlet times v theta, and this is all still times z hat. But we know all of these items right now, so we can just write this is equal to, let's see, the density we're going to take as 1,000 kilograms per cubic meter. Q, we've been told, is 20 cubic meters per second. The radius of the outlet of the stator is 0.8 meters. And v theta we found up above to be 1.754 meters per second. I don't even think we have to do any canceling here because the meters, conversions here, because we get the meters cubed canceling, so we get kilograms, kilogram meters per second squared, which is newtons, and the leftover meters, so we're going to get Newton meters out of this. And when we do the multiplication all the way through, we get 28.1 kilonewton meters. So okay, so we've been carrying through formally the z hat all the way through. Of course, the torque is the only component we're worried about is the torque in the z hat direction. So now we can take the scalar value of torque is equal to 28.1 kilonewtons per meter. And I'll leave it to you to figure out what the power is, what the rate at which work is being done on or from the stator on your own.